solve this system. So in other words, I can solve this system Ax equal to what do you call lambda x. So the Ax is going to be, so this is going to produce what you call a system of equation x1 plus x2 equal to lambda x1 and x1 plus x2 equal to what do you call lambda x2. Okay, and if you simplify these two equations, what does these two equations are telling you? Okay, so you can deduce from these two equations. If you, for example, subtract these two equations, you're going to get x1 minus okay. So if you subtract these two equations, what you're going to get? You're going to get lambda times x1 minus x2 equal to 0. So this is what that you're going to get. You're going to get that lambda x1, okay, lambda times x1 minus x2 equal to 0. And now, when the product of these two numbers is 0, so you have the two cases that either lambda is 0 or x1 is equal to what do you call x2. Okay, so if lambda is 0, okay, if lambda is 0, then x1 plus x2 is the only constraint imposed by. So if the lambda is 0, then these two equation tells you that x1 plus x2 is 0. Okay, so in other words, x1 is really minus x2. So in this case, what you're going to get, your x, which is a vector x1, x2, will be a vector, say x1 and minus x1. So you can say that this is a vector that is spanned by 1 and minus 1 times x1 actually. So this is what that you're going to get. So this is really the vector x. And so this is what that you're going to get. So in other words, you're going to get a vector x1. So corresponding to this condition, if lambda equal to 0, you get the vector 1 and minus 1 actually. Okay, so you got this interesting vector, or you can get minus 1 and 1, doesn't matter. Now the other case is, okay, so this is the eigenvector corresponding to lambda equal to 0. The other case is that x1 minus x2 equal to 0. So this is the second case. So if the x1 minus x2 equal to 0, that means that x1 is x2. Okay? So if x1 is x2 and lambda is, for example, is any number, okay? So if lambda is not 0, that means that x is a vector. So if x1 is x2, what does this is going to give you? So if x1 is x2, so this is going to be 2x1 equal to, so from say first equation you're going to get 2x1 equal to say lambda x1, okay, 2x1 equal to lambda x1, and say for example second equation you're going to get 2x2 equal to what do you call lambda x2. And once you have this, what does follow from here? That you have lambda equal to 2. So we got another eigenvalue for it actually. So you got a value lambda equal to 2, and corresponding to this you got an eigenvector which is x1, x2. For this eigenvector, so if they both are equal, so it's going to be x1, x1. So it's going to be 1, 1, x1 actually. So the eigenvector corresponding to this, in other words, the v2 that you get is really the vector 1, 1. Okay. Now what would be the physical meaning of these two vectors? So the first equation, so you got two values. So one thing, so you got one eigenvector 0, v1. In other words, it satisfies what do you call, a v1 equal to 0 times v1, okay, and the eigenvector corresponding to say 0 v2 is corresponding to say a v2 equal to 2 times of v2. So this is what that you're going to get out of these results. So let's try to visualize. My task, is not at the moment is to do the solution of all this. So just went through these, these simple calculations actually, but I want to visualize this. So for example, if I take now x1, x2 axis or xy axis, and I take, for example, a vector v1. So how does where does the v1 is going to locate actually? So the v1 is 1 and minus 1. Okay, so 1 and minus 1. So if x1 is 1, y1 is, x2 is minus 1. So 1 and minus 1. So if this is 1, so maybe this is the vector. So this is the vector v1. Okay. Now what is vector v2, which is 1, 2. Okay, so 1, 1. So it's going to be some point here. And this is really the point 1, 1. So this is my vector 1, 1 minus 1. This is my vector corresponding to the point, say 1, 1 actually. Okay. So the picture that you're going to get is really this rectangle. Okay. So this rectangle. Now if on this rectangular region you apply the matrix A, what are you getting? Okay, what are you getting as output? So if this is x1 axis and this is x2 axis. So what is happening with say this vector v1? Okay, so what is happening with this? This is vector v. So this is v1 and this is v2. So what is happening with vector v1? This v1 becomes 0 times v1. So in other words, this vector is projected, is annihilated, and for example thrown here actually. So it becomes 0 vector. And what does this v2 vector become? The v2 vector become, what do you call, the vector twice of v2. So if this is say 1, 1, okay, so it goes up to say 2, 2 actually. So this is really the vector 2v2. Okay, so this is vector 2v2. So what happens with this rectangular region? Okay, so what happens with this rectangular region? In other words, when you apply the transformation A to it, this entire region is being thrown or projected or transformed into this vector actually. Okay, into this vector. So in other words, it's kind of first collapsed into a single vector and then extended actually. So this vector collapsed to 0, and this vector v2 kind of extends. So it gets twice actually. So it gets a double size. Okay. So this entire region is collapsed onto, what do you call this second vector? And I would like to similarly make some more pictures. I'll not do calculations directly, I'll directly write what do you call the results. Okay. So let's do some more visualizations. So let's take for example a matrix A that goes like 1, 0 and 1, 2. Okay, 1, 2. So what you can basically say that for this vector you will find 2 pairs. By repeating the calculations you will find 2 pairs. So one pair is really one pair is really 1 and vector v1, where the v1 is vector 1, 0. Okay, so it's vector 1, 0. Okay, so this is the first eigenpair that you're going to find corresponding to it. Okay, and the second pair that you're going to find corresponding to this is the eigenvalue 2. Okay, and the vector that you're going to find is really the vector V2, and this V2 vector is vector 1, 1. Okay, this is what that we're going to find. So what does this show? This shows that the vector AV1 becomes V1, so it doesn't changes actually under the transformation A, and the vector V2, okay, becomes AV2 becomes really the V2 twice of the vector V2 actually. So if you would like to, for example, transform this vector, so where is going to be 1, 0? So 1, 0 vector. Okay, so 1, 0 vector is really this E1. So this is really my vector V1. And what is a V2 vector? So the V2 vector is vector corresponding to this point, which has coordinates 1, 1. So it's really the position vector of the point 1, 1. Okay. Now what would be the region, for example, spanned by these two vectors? So it's going to be this rectangular region. This is the rectangular region. Now what happens with this region when you try to transform this under the transformation of the matrix A? So when you're going to transform it, so what do you think what you're going to get? So the V1 stays V1. So the V1 stays V1, and V2 becomes a double actually. Okay? So the V2 becomes double. So if this is 1, 1, it becomes double. Okay? So this is really the vector 2V2. And if you see what will happen with it, so now this rectangular region has been a bit stretched actually. So the width is not changed. Kind of its height is changed, it has doubled. So this rectangular region has been transformed into, for example, this region. Okay, so the rectangular region has been transformed into, say, this region A. So if you, for example, put a circle here, okay, so this circle would be horizontally same, but it would be vertically, vertically stretched actually. So it would look like something like this actually. So it has horizontally same radius as this, but vertically it has been stretched actually. So that is the kind of a transformation. So what does you see from all these examples, that every matrix transformation or every matrix, okay, if you for a given matrix, if you know the eigenvalues and eigenvectors, you can actually see its physical effect actually. You can actually see its physical effect, that if you apply it on a given region or a given set of vectors, okay, how that region would be transformed under the matrix A or under the transformation of the matrix A actually.